Hey guys, so today we're going to talk about graphs of numerical data. So in the end of last unit, we talked about how we did graphs and talked about graphs and compared graphs of categorical data. So today we're going to start looking at numerical data and how we deal with that. There are a lot of ways we can graph numerical data. In general, numerical data is a little bit harder to graph because it's not as clear cut and already in really easily defined categories. It's numbers, and numbers have a lot of variation to them, and so the way we deal with them in terms of graphing and describing is a lot different, and there are a lot of ways that we can do it. So today's objective, we're going to be able to graph and describe distributions of numerical data. We're going to specifically look at two different types of graphs today, a dot plot and a histogram, and in future lessons we will talk about other types of graphs that we can make with numerical data. So, there we go. So we're going to start with, this is a set of data. This is a sample of some of the data from the survey I had you guys fill out at the beginning of the school year. This is a question that asks, how afraid of heights are you on a scale of 1 to 10? So this is just a sample of your answer. So let's say I wanted to draw a quick graph of that data where I put those numbers on some type of graph so that I could get an idea of what the patterns, what the trends are in terms of what people are answering for afraid of heights. So one graph that I can make is called a dot plot. So a dot plot is probably the most basic, the most simple way that I can represent graphically or visually numerical data. It's pretty quick and simple to make, and it works really, really well for relatively small amounts of data. So like 50 or less amounts or like numbers in our set of data works really well here. So what it is, all I do to make a dot plot is I would just draw a number line on my paper. I would, number it starting from the beginning and the end. In this case, I might number my number line 1 to 10 because that's what my data can go through. And then I would simply just put a dot above the number line for each time a number appears. If it appears more than once, I put another dot, etc. So I end up with this dot plot that shows me, generally speaking, what people are answering for this question. So I see that I have a lot in this kind of lower 1 to 3 range, and then I get a lot in the 6 to 8 range. There's not as many in between, right? So I get a quick look at my data and what the patterns are and what the trends are with this set of data. So dot plots work really well for on a piece of paper if you want a quick representation of data. But when we start getting with larger sets of data, in this case, I have a whole bunch of numbers. These are like GPAs for a bunch of students on a single dot plot. It starts to get a little hazier. And so when you look at this picture, I always ask my students, like, what does this look like? I'll let you think about that for a second. The most common answers I get are, it looks like fire, or it looks like the Disney castle. Those are the two that I get the most. So if you thought one of those things, you are not very original. Sorry, just kidding. So the problem with this is that it's too much data for a dot plot. There's a lot going on here, and it's just not the best representation. Plus, that takes too long to make. Clearly, this was made with a computer program, and if I have access to a computer program, I can probably make a better graph that is a little bit less headachy to look at. So instead, I might make something like that we call a histogram. So histogram is this type of graph. It kind of looks like a bar graph, except you may notice the bars are all touching now. They don't have gaps in between. And of course, my x-axis is numbers instead of categories like they were before. So histogram gives us a little bit of a cleaner look to that same set of data. So let's talk about how a histogram is made. This is not something you would make on your own on a sheet of paper. This is something that computer programs make, but you'll be given a lot of them to describe and talk about in this class. So just real quick, to talk about how a histogram is made, I have those same set of numbers. First thing I would do is to make some type of frequency table where I decide what my categories are going to be. So in this case, I decided my bins or my categories are going to be people who answered from 1 to 2, from 3 to 4, from 5 to 6, and from 7 to 8. When I create these categories, I want my bin or my bin widths to always be the same. So in this case, I went by 2s. If I wanted to, I could have gone by 3s. 1, 2, 3, 4, 5, 6, 7, 8, 9, and had 3 categories, etc. So I create these bins, and then I count how many people or how many numbers are from 1 to 2. So I counted those up and I got that there are 7. There are 7 1s or 2s. And then I counted for 3s or 4s, for 5s and 6s, for 7s and 8s. I just counted how many were in each of those bins or categories and put the frequency right here. And then from there, we're basically making a bar graph where each bar or bin represents one of these categories that I created. So this first bar or bin is the 1 to 2 category. The second one is the 3 to 4 category. This third one is the 5 to 6 category. And this last one is the 7 to 8 category. So I end up with this histogram. The x-axis is numbers, like I said before. So I can see like the span of numbers that each bar is representing, and then I have the height of the bar representing how many frequency, like how many numbers or how many people are in that category. So just as a quick little recap on histograms versus bar graphs. So a histogram is for numerical data. We have numbers on the x-axis and the bars are touching. Whereas on a bar graph, which is for categorical data, we have categories on the bottom and the bars are not touching. We have gaps in between the bars. So that's important to know the difference. They kind of look similar, but when we actually look closely at them, we can tell which is for numerical and which is for categorical data. So let's look a little bit closer at a histogram and how it's made. So this is a set of pre-AP Algebra 2 test scores from many, many years ago, like many, many years ago. I just keep using the same graphs every year. This is a dot plot of that data. So we can see that we had one person who made like a 54, and then we got a lot of people in this like 70 to 80 to low 90 range. And we have a few people up in this higher 90s to 100. So if I take that same data and turn it into a histogram, it might look something like this. So notice that with a dot plot, I can actually kind of tell exactly what the grades were for the different students. Whereas on a histogram, I have a little bit more vague information, but it's also a little bit easier to look at. So how I would read a histogram is, for example, this bar right here is going from 65 to 70, and it has a height. That bar has a height of 3. So that would tell me that 3 of the test scores in this class were greater than or equal to 65, but less than 70. That's typically how histograms work. It starts at the first one and goes to just below that next kind of boundary. This last bar over here is between 100 and 105. And it has a height of 2. So that would mean that there are 2 test scores that are greater than or equal to 100 and less than 105. Okay, so remember that with a histogram, or keep in mind with a histogram, we don't know exactly what these people made on the test. So for this bar down here, I just know that those three test scores were in that range. So they could have all 3 been a 65, or it could have been 166, 167, 169. Same up here. They could have both just been 100. But maybe there was extra credit and one of them was 104 or something like that. We don't know exactly what the scores were or what the numbers were, but we know the range, and we can kind of see this overall picture of what was the most common grade, what was the least common grade, is there any numbers that seem out of the ordinary. Like, we get kind of a general picture of what the data or what the graph looks like by looking at this histogram, even though we don't know the exact numbers. I want to show you a series of graphs that kind of show you what happens when we change the bin width. So I mentioned those bars, you're kind of setting your categories. So in the example that I use, I set my categories as like from 1 to 2, 3 to 4, 5 to 6, 7 to 8. I can make those bins or intervals or categories wider or narrower just based on my needs. But that is going to affect how the graph looks. And that is something that could be good to know. So I have this dot plot. This is showing how much sleep people got on a weekday. This was also from that beginning of year survey I did with you guys. So we have how much hours of sleep people got on a weekday as a dot plot. Here's that same data as a histogram where the bin width was 0.25. So that means each bar, for example, this one right here is between people who said they got between 3.5 and 3.75 hours of sleep. So we can kind of see that data as a histogram with really tiny intervals. Here's that same data with a bin width of 0.5. So like this bar right here is between 4 and 4.5. So how many people got in that range of sleep? There's that same histogram with a bin width of 1. Right, so this would maybe be from 6 to 7, from 7 to 8, etc. Here's that same histogram with a bin width of 2. So I want you to kind of notice what's happening here, right? This is a little too hard to read and it's too like specific, right? So I make it easier to look at, easier to understand what's going on with the data. But then at some point, it's starting to get a little bit more vague and like, it's a little harder to tell what's going on here. It's harder to see some of those trends and patterns. Here's a bin width of 6, right? So anybody who said between 0 and 6, anybody who said between 6 and 12, very unspecific, very vague. So the bigger my bins get, the more vague that histogram looks, and it's not giving me as much information. But we also don't want to have a histogram that's, too small, because then there's just too much going on and it's hard to look at. So when we kind of decide bin widths, we want to be somewhere in the middle. Generally speaking, we want at least 5 bins in terms of our data. So when we have less than that, it starts to look a little bit weird. So the biggest bulk of today's lesson is talking about how we describe numerical distributions. So most of the time you are given a graph to look at, especially for histograms. It's not something that you are spending a lot of time creating, but you do need to know how to describe those histograms or describe those distributions, and there's specific things you have to mention when you're describing them. So to help you remember what those things are, I have a little acronym for you. Our acronym is, we're going to learn today how to cuss and BS. So those letters stand for something, obviously. So C in cuss stands for the center. We're going to talk a little bit about this and look through some examples, but center means where are the peaks or modes in the graph. Second, or the U we'll come back to. The S, the first S is shape, which means is the graph symmetric? Is it skewed? Is it uniform? We'll talk about what all these words mean in a sec. The second S stands for spread, means basically how spread out is the data, what's the min, what's the max, what's the range. And then the U, going back to that, stands for unusual features. Are there gaps? Are there outliers? And then BS stands for be specific, which for us means include context. Talk about the actual data and variables in the problem. And this is the biggest thing that I end up counting off points for in this unit every single year. Just forewarning you. So let's start with center. So starting with center, generally when we talk about center, at least for a histogram, we're typically going to talk about where the peaks in the graph are, where the modes are. So if you remember back in middle school, mode is like the number that appears or the data that appears the most often. For our sake, we're going to think of a mode or a peak as where do we see a really, really tall bar that has shorter bars all around it. So kind of like a mountaintop peak, the peak of the mountain. So in this case, I see a peak in the graph at about 5 letters. So our center, our peak or mode, is happening at about 5 letters. This is the survey question that asks how many letters are in your name. So generally speaking, kind of the average, the center is about 5. This particular histogram, we would say is, go back, unimodal. So unimodal means that it has one peak or one mode in the graph. So there's one mountain peak. So if a distribution has more than one peak or mode, we call that a bimodal histogram. So a bimodal means that we have maybe 2 places where there's a tall bar and shorter bars around it. Notice that this peak or mode on the left is not as tall as the second one, but we would still call that a peak because it is much taller than the bars around it, and we definitely have a very obvious dip in between. Sometimes you have bars that are really tall, maybe the same height, but are closer together. We don't always call it a peak. One thing to think about if you want to call something bimodal, you do need a little dip in between. If you have 2 bars that are right next to each other that are about the same height, that's not bimodal because there's no dip in between. In order for it to be bimodal, we need a pretty obvious prominent dip in between. Think about if you were to draw your finger over the shape of the graph really quickly, would you dip down in the middle or no? If you're not going to dip down in the middle, that's not bimodal. Those two bars would technically be the same mode. Another thing to keep in mind, if you are going to call a distribution bimodal, you should be listing two peaks or modes. So center is about telling me where's the peak or mode in the graph. Is it unimodal or bimodal? If you're saying it's bimodal, you should be telling me two modes. Otherwise, and we'll talk about this in later sections, but another thing you can list for center would be the mean or the median. But from a histogram, it's really hard to calculate the mean and the median. So that's why we usually stick with peaks and modes as our measure of center. Let's move on. If a histogram has no obvious peaks or modes, if all of the bars are roughly the same height, we call that uniform. So if there are no peaks or modes or obvious peaks or modes where a bar is way taller than the ones around it, if all of the bars or bends are about the same height, we call that uniform. So that's center, right? It can be unimodal, bimodal, it can even be multimodal if it's more than two modes. It can be uniform, and remember, center for a histogram, we usually list the peak or mode in the graph. So that's center. So now we're gonna go to, come on now, shape. I always save unusual features for last. You can do them when you're writing them in whatever order you want. So shape is one of several options. Technically, unimodal, bimodal it could also be mentioned with shape, but you can mention it with center as well. But with shape, we're usually wanting to know, is the graph symmetric or not? So symmetric would mean that if we fold it in half at kind of the middle place, that it would look roughly the same on either side. So we can kind of see here, if I kind of find the middle of my set of data of my x-axis numbers and fold it in half right there, my bars look roughly the same on both sides. It's not exactly the same, it's not perfect, but it's pretty close. So most of the time when we call something symmetric, we're going to say that it's approximately symmetric or roughly symmetric, unless it really is truly perfectly symmetric. That's very rare in real life with real data. Is it going to be perfectly symmetric? So we usually say something like approximately or roughly symmetric. Right, so we're not going to be too perfect about this. If it's roughly the same on either side of that center line, then we call it symmetric or roughly symmetric. If it's not symmetric, it's going to be skewed. So if you're not saying it's symmetric, you're saying it's skewed. So skewed, and we always mention a direction. Is it skewed to the left or skewed to the right? Skewed means that wherever kind of your peak of the graph is, you have more bars that are like shorter and more stretched out. We call that like a tail. There's a tail on one side of the peak or another. So it's not symmetric. It's not even on either side of our peak or either side of our center. It's more stretched out on one side or the other. The direction of the skew is going to be towards the direction of the tails. So for example, this graph on the left is skewed to the left because we have the shorter tail stretched out thing is happening on the left side of the peak. This is ages of people, female cardiac patients. So most people who are cardiac patients, most females who are cardiac patients are in the higher ages, in the 70s range, and there are fewer cardiac patients that are in the younger ages, right? So it's skewed to the left. Skewed to the right is the opposite. We have kind of that longer, thinner tail on the right side of the graph. The peak is more towards the beginning, and the tail is dragged out to the right. So skewed to the right or skewed to the higher numbers, this is the charges, like the amount of money charged for female cardiac patients, right? So we have our tallest bars in this kind of $7,500 range, and then we have a few people who are charged a very, very large amount of money. So skew to the larger numbers. Be really careful when we use the word skew in statistics, we're referring specifically to the shape of a graph. So from now on, we shouldn't be saying things like, oh, the bias makes the data skewed, or this is skewing the opinions of people or whatever. So when we talk about skew, we really should be only using that word to describe the shape of a graph. Okay, so then we talk about spread. Spread is really easy. Spread is just basically either saying the range, like what's the highest number minus the lowest number, or just reporting the minimum and maximum values. So I can kind of see that for mothers' ages, this is the question on the survey about how old was your mother when you were born. So the mothers' ages are going from like 17-ish, maybe 18. I think that's 17. 17 to like 43. Or I could just say the range where I subtract highest minus lowest. Either one is fine. We're just explaining or saying how spread out the data is. Same thing with the father's ages. And we'll talk about this in a couple minutes, but when you have an example where you are comparing two sets of data, like we might be comparing the mother's ages to the father's ages, for spread, we would want to make sure and say which spread is wider or narrower, or which range is bigger. That's really important. So range is really easy, or spread's really easy. And then we're going to talk about unusual features. So unusual features could be kind of two main things we're looking for. The first would be, do we have what we would call outliers or possible outliers? So in this case, this is the number of people per household, I believe. Yeah, so number of people per housing unit for a bunch of different cities, like the average number of people per housing unit. So I have most of my data is going from 3 to maybe 4-ish, or just under 4, 3.5 maybe. But we do have a couple of cities that are way over here in the closer to 2.6 range. And it's pretty far removed from the majority of the data. So that might be what we call an outlier. An outlier is a value or a bar or a bin, or on a dot plot it would be a dot, that is pretty far removed from the majority of the data. It's a good idea right now, especially with histograms, to call that a possible outlier. We'll talk later in a different lesson about how we would actually test for outliers, but even then, that's usually more when we're doing different types of graphs. So on a histogram, we're almost always going to say it's a possible outlier. And then the other thing we could be looking for is gaps. So sometimes a graph would have gaps kind of in the middle of it. So not necessarily a gap because of an outlier, but if there's gaps in the middle of the data, that's interesting to know. That's something that's unique that we would want to mention and talk about. So in this example, we're looking at the number of miles driven by automobiles in New York City. So going from like 0 to a little bit above 40,000. And we have a little section of the graph here, and then another little section of the graph here. And then there's like nothing in the middle. So there are no cars, there are no automobiles that drive between 20 and 30,000 miles. So thinking about why that might be is something we would want to know. So talking about gaps in the middle of the data is important because we would want to know, like, why? Why is there a gap in the middle of the data? And then the BS in this little acronym, custom BS, means be specific, and that means you want to include context. So when I'm describing graphs, I'm never just going to say numbers. I'm never just going to talk about center shape, spread, unusual features. I have to mention the variable that I'm talking about and the actual like population context that I'm talking about. So give it context always, 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 always. So let's practice, and we're going to go through these fairly quickly just to give you an idea of what this looks like. So in this histogram, you can pause it right now if you want to practice and think about center shape, spread, unusual features, and being specific. Try to be in as complete sentences as you can. So for this one, the center, I would say that the distribution of for hours of sleep, this is how many hours of sleep people get a night, is at around 7, because that's where my tallest bar is. For the shape, I would say it's unimodal. There's one peak and roughly symmetric. Maybe have this one little guy over here, but for the most part, roughly symmetric. For the spread, it's going from 0 hours of sleep up to about 11 hours of sleep, or you could say it has a range of 11 hours. And then unusual features, I'm going to mention there is a gap from the 1 to 3 range, and there's a possible outlier at 0 hours of sleep. For the second example, I have quiz grades. So for center, I would probably say this distribution is bimodal, which means there are 2 modes or peaks, one in the 50s and one at around 80. For shape, again, I'm saying it's bimodal. I just mentioned that again. But it is roughly symmetric around each mode. This is one thing that you can say if you have a distribution that's bimodal, that might make it hard for you to describe the shape of the graph overall. Maybe overall this is skewed to the left, but I could also say something like it's roughly symmetric around each mode. That might be easier to talk about on a bimodal graph. For the spread, I would say it goes from the mid-30s to the mid-90s, the grades. And then unusual features, I could say that there's a gap in the 40s. I might also mention that we have a dip in numbers and frequency in the mid-60s. There weren't as many people in that range. And then we do have a possible outlier at about 35. Right? So again, we want to make sure that we're talking about context. So noticing that I'm mentioning quiz scores somewhere in that description. You don't have to mention it at every turn, but somewhere in your overall description, you should mention the actual variable you're describing. For this one, this is the number of shoes people said they owned on the survey. So I could say the center is this like 5 to 10 range, maybe about 8 pairs of shoes. The shape, the distribution is definitely skewed to the higher numbers or skewed to the right. For the spread, it goes from about 0 to about 40 pairs of shoes. And this one doesn't really have any unusual features. So if you don't have unusual features, you can just skip that part, or you can say there are no unusual features. And something I did really poorly on this description is nowhere in here did I mention shoes. So this would lose points if this is what I answered on a test or a quiz. So make sure you are mentioning context. If you are asked to compare two graphs or two sets of data, same thing, center shape, spread, unusual features for both graphs, but comparing doesn't just mean listing facts about both things. Comparing means telling me how they relate to each other. So most specifically, we want to make sure we compare center and spread. So tell me which center is higher or lower than the other. Tell me which spread is wider or narrower, or which range is bigger or smaller. So using those comparison words is really important. So for center, I might say for the male hours of sleep, the center is at about maybe 7 hours. But for females, it's maybe a tad higher, but pretty close to 7. So I could say that the center for both is about the same at about 7 hours of sleep. The females maybe have a tiny bit lower, potentially, but it's about the same. For shape, I would say that the male distribution is definitely roughly symmetric. The female distribution is a little bit more skewed to the left, but you could also possibly call that roughly symmetric and just mention these two values as outliers or possible outliers. I would take symmetric on that one. For spread, I'm just gonna list the minimum and the maximum of each and compare how wide they are. So I would say for the males, it goes from 3 to about 11, whereas the females goes from 0 hours to about 10 hours. So the spread for females is slightly wider than the spread for males. So comparing them, saying which is wider or narrower. You could also mention that overall the males distribution for hours of sleep is slightly shifted to the higher numbers. Unusual features, I would mention that the female distribution has a couple of possible outliers below 2 hours of sleep, and the male distribution doesn't really have anything. So that would be an example of how I compare. So just as a recap, and then we'll be done for today because I know this one was long, it's really, 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 really important that you are descriptive and specific and that you use comparison language if you're actually comparing two sets of data. So talking about higher, lower, wider, narrower, etc. That's what comparing means. So I think that's about it for today. I'm going to let you stop watching this video and let me know if you have any questions.